All right. So welcome to day 3 of NeuroHackademy. This morning, we're going to be talking about your week 1 mini projects. So you may have noticed that at some point last night, you got assigned into a new Slack channel. And that Slack channel will be something like mini-proj-group 1 or group 2 or group 3 or whatever. So you have all been assigned into groups. And the first thing I want to do is show you where, if you didn't get an invitation or anything, where to find this. So if you go to the Jupyter Hub and you go to your home directory, and then navigate into the shared directory and the docs directory, there should now be a mini project groups notebook in here with all the other documents. And if you open this up, this just has a list of the groups and who's been assigned to them. It is possible that we missed someone, or that we've assigned someone to a group that doesn't work for them. If that's you, please let us know as soon as possible. And what I mean by a group that doesn't work for them, we have one group of everyone who's in a really remote time zone. And so if you're joining us online and you didn't get assigned in there and you wanted to be assigned in there, just let me know, or vice versa. Everyone else, we're assuming if you didn't fill out that Google form about time zones, we're assuming you're joining from our time zone in the Pacific time zone, or you're close enough to be synchronized with us. So everyone else, aside from the Zoom group, we're assuming you're in our time zone. But let me know if you want to change that. Okay, so again, if you don't find yourself, just let me know. The channel for each group, the channel for each group is just listed below the name, and you've got a place to meet in terms of an owl and a meeting room. And basically what's going to happen this morning is I'm going to spend about a half an hour, hopefully, going over the project and what we're kind of expecting, and the timeline, and then we'll let you all go find your groups and start working on them. If you look at the schedule, there are a few time slots allocated for these projects. So there's this morning, there's some time this afternoon that also overlaps with the optional CHN tour, the Center for Human Neuroscience tour here. Just to talk about that really quickly, I believe at 5 p.m. there's sorry, let me just look at the schedule. Yeah, from 3:30 to 5 p.m. That's time for you to work on the mini projects, but it's also, there's going to be a Center for Human Neuroscience visit. So John Piles, who leads our Center for Human Neuroscience, which is our fMRI center, he's going to give a tour of the center and do a quick scan of someone if there's a volunteer to do an MRI scan. And he'll talk a little about MRI physics and some of that kind of stuff. So this is actually a great opportunity, especially if you don't have a scanner at your university, to kind of get a little bit of experience with that. So I do encourage you to go to the Center for Human Neuroscience visit if you're interested. For anyone who's already running scans and doesn't find this to be very exciting, you're welcome to stick around and work on the week 1 projects. There's also some time allocated on Friday morning and on Friday afternoon to work on the projects. And we'll on Friday morning, we'll discuss just how you're going to submit your final projects to us. Otherwise, it's up to you to find time, and I'll just be very clear about this. These projects are made with the purpose of helping everyone practice the technology, practice working in a group, getting to know some of the kind of tools we're going to be using next week, and kind of getting a little bit of experience working with data. So you only have a few hours to work on these projects realistically. We are not expecting you to change the world in that time. So please don't get really stressed out about these projects or anything. I'll show you in just a minute the very simple version that Ariel and I came up with to solve this project, and you'll see that it's not very complicated. Okay, before I do that, any questions? All right. So the way these projects are going to work is if you first of all, just take your browser and go to github.com/NeuroHackademy2025/ well, just go there. This is just the GitHub webpage for our NeuroHackademy 2025 group. You should all be part of this page. And in fact, if you didn't get assigned into a project group, it's probably because you haven't accepted our invitation into this GitHub organization. If you click on the repositories, there are a bunch of repositories here. Most of them aren't very important for you, but there's one here called the Week 1 project template. If you click on that, you'll come to a GitHub repository, and you may notice that in the upper right corner, there's a big green button that says use this template. So my recommendation here is that once you get into groups, you nominate one person to be kind of your GitHub custodian, and you'll have them fork the repository and then add all the other group members as collaborators. That's my recommendation, but you don't have to do it that way. If you'd rather everyone fork the repository themselves and do pull requests to each other or something like that, or work in like subgroups, that's all up to you. But regardless, at least someone's going to need to click this use this template button and create a new repository. And you'll come down here and it'll basically say, let you choose. I mean, if you're a part of multiple groups like I am, you can choose which group you fork this into, but you want to fork this into your own username or your own GitHub space. And I'm just going to call this Week 1 project. And then we can just create this repository. Now, I don't think we got to forking in all the GitHub sessions. So if you're not sure what forking is, basically, if you've got a repository, if I have a repository and you want to have a copy of it, you can fork my repository and it makes a copy of my repository in your GitHub account that you then have permission to edit and everything. And once you've made some changes, GitHub is very good at tracking what your changes are relative to my original repository and can do things like merge them back and forth. Don't worry too much about this. We'll talk about GitHub on Friday and how you're going to submit the projects and that kind of thing. But the point is that once I've used this template, I now have a Week 1 project that is an exact copy of that project in my GitHub account, in Noah Benson Week 1 project. Okay, questions? Okay, so now that I've made a copy of this project, I can go back to the Jupyter Hub. I'm going to go back to my home directory and launch a terminal. And here I can just git clone git at github.com : and then my username, Noah Benson /Week 1 project, the repository I just made. And this will make a Week 1 project directory here for me. Okay, and then we have this this repository here. Now, I just want to say that the README here contains some detailed instructions for all this. So if you're not sure what to do, the README has instructions. I'm going to talk about all this, so we don't need to read them right now. But if you come back later and you're confused, you can review these in the README. There's also this, well, I'll go through the repository now. Okay, so there's a few files here, and I'm just going to talk about them all briefly. The main and most important one is this analysis.ipynb file. This is just a notebook where we kind of set up the problem, and I'll talk through the problem in a minute here. And wrote up our own solution to the problem, and we'll get to that in a second. My expectation is that you'll modify this notebook, or maybe make some notebooks of your own, and eventually come up with a workflow kind of similar to ours, but using a different method or something like that. There's a couple directories here. The results directory you don't need to worry about right now. We'll talk through it on Friday morning when we tell you how to submit the final project or your project results. There's an src directory here and a pyproject.toml file. If you decide you want to write a little like Python code in like a library, you can put it in this src directory, and there's some instructions on how to use the pyproject.toml file. You don't need to do this. You're welcome to just work in notebooks, and that's totally fine. This is sort of up to you if you want to try to make a little library as part of this project. So really the most important thing here is the analysis.ipynb file. And it additionally has a bunch of instructions in it that kind of talk or walk through all the components we decided to include as part of our project. Okay, the next thing I'm going to do is in just a minute here is to talk through this notebook, and I'll just explain what we did in our project and what the project is. But before we do that, I'm going to introduce a library to you. And some of you, depending on which sessions you were in yesterday, have already seen a little bit of this library. But I want to make sure everyone has at least a bit of an introduction to it. So I'm going to go ahead and create a new Python notebook just to explain this very quickly. You're welcome to create a notebook and follow along, up to you. Okay, so when we're dealing with files in Python, there's a lot of ways to do this. You may have seen the open function where you can give open a file name and it gives you back what's called a file handle or a file object that you can read and write from, like read data from the file system. There's a library that helps you manage file systems in general, and it's called pathlib. So if I say import pathlib, or in fact, what I really think I want to say, rather than import pathlib, is from pathlib, import path. Okay, so on the file system, paths just refer to file names or directory names, something like /home/Jovian. That's your home directory is a path to that directory. And so we can create a path object by just giving this path type a file system path. So I'm going to make a path object here. And these path objects have a whole bunch of really nice features. So for example, I can ask, is this a directory? And it'll say yes. And I can ask, is this a file? And it will say no. I can, for example, make a list of all the contents of this directory by calling the iter for iterate directory method. And it'll give me back a list of paths. It says POSIX path because we're on a POSIX system. These are all just path objects of all the contents of this directory. And these are also paths, so you can then like query them and look inside of those directories. These path objects are just a really handy way to look at the file system and to deal with files and to navigate directories and things. You can also, so for example, let me find a good example. I've got a git config file here. I can be pretty sure that's a text file. So I'm going to show you how to read it in and print to the screen, basically. So we created this path object P. And if I want to find a file inside of a path object, I use the / operator, kind of like it was a directory and I was putting another slash in a new file. And I can say .git config. And this will give me back a path of that .git config file. So I'll make a variable called gitconf and say, just to make sure I got it right, is this a file? Okay. And now I can say with gitconf.open as f print f.read. And that's just going to print out my GitHub or my Git configuration file. These are just the contents of that file. Now, if this is a new construction to you, if you haven't seen this before, what this is saying is take that file and open that file so that I can read and write to it from it. And we're going to call that file f while it's open. This whole with clause is basically, it's basically a way of making sure that that file gets closed when you exit the with. So even if you raise an error inside of this with clause, it'll still close the file. And that's kind of an operating system hygiene thing. You want to make sure you close the files you open. If you get too many files open, you can cause problems with your program. Okay. A lot of libraries like pandas, for example, will read from these file handles. In fact, many libraries read only from these file handles. You can't necessarily give them a path. But regardless, you can use this kind of construction to read files this way. Okay. The reason I'm telling you all this about these paths here is because there's another library that's not pathlib, but cloud pathlib, which is specifically for reading things that are in the cloud, like on Amazon S3. So I'm going to say from cloud pathlib import import something called S3 client. Now cloud path, as you might guess, is basically analogous to path, except it's going to be a path in the cloud, like an S3 path. And S3 client is just an object that kind of manages our connection to the S3 server. If you're new to S3, S3 is Amazon's kind of storage system, cloud storage system, where you can put lots of where you can put files, and it's fairly cheap to store lots of data there. Amazon gives all those files a path. So your S3 path will have a bucket name, For example, the natural scenes dataset has the bucket name S3:// natural scenes dataset. Oops. This is the S3 path for the natural scenes dataset bucket. And so what I want to demonstrate here is that we can make a cloud path by saying cloud path. We're going to pass it this S3 address. And then we just need to give it a client that maintains the connection. So we're going to say S3 client as the second option. And we just need to give it one argument here, no sign request equals true. Now, this no sign request, the natural scenes dataset is a public S3 bucket, so you don't have to authenticate when you read it. And if you try to authenticate, Amazon will give you an error. So what this is saying is, hey, Amazon, or hey, CloudPath, we're going to connect to S3 using a client that's not going to try to authenticate itself. And if we do that, that'll create this CloudPath object. It's an S3 path here. And we can, for example, do exactly what we did earlier, where we make a list of the contents of this directory by iterating over the content by using the iter_dir to iterate over the directory. And you'll see that it'll give us back a bunch of S3 paths for all the subdirectories in this S3 bucket. And just like with the normal paths, there's functions like cloudpath.isdir and isFile, and you can open these files and it will open them as if they were on your local hard drive. You can also, and this is honestly maybe the more useful way to use this sometimes, there's a function in the operating system module called fspath. Whoops, from OS import fspath, stands for file system path. It'll try to convert something you give it into a file system path. And so you can say, for example, let's take this index.html file here. I can say, I can get the index.html file from the cloud path here, just like we did earlier, where we used a slash to separate the directory and the file. And that gives us back the cloud path for this file. And then I can say fspath on this file, and it will make sure and download that file into a temporary directory and then give me the path to that temporary directory. So this file is now downloaded here on my computer. And in fact, if I just copy this and go back to the terminal and cat it, you'll see that there's the contents of that index.html file. So this is a way to ensure that you've got files from some online data set locally on your computer. And since most of the stuff we're going to deal with is going to be on Amazon S3, and we'll talk more about this on Friday, but this will let you access pretty much anything. And since our hub is also running on Amazon S3, all of this is very fast, and downloading these data is pretty fast. Yeah.
We need temporary folder sometime, or is it automatic?
Great question. Yeah, do we need to clean the temporary folder sometime, or is it automatic? I believe it gets cleaned every time you restart your hub. So you don't need to worry about it. We have a panel where we watch your home directories to make sure you're not using too much space, and we'll let you know if anyone's directory seems to be getting too big. Something I didn't mention here, but I'll talk about in just a second, is that you can also give this a local cache directory, where you say, basically, I want you to cache everything in like my home directory so that later, like tomorrow, it's still there if I want to read it again. And that way it doesn't have to re-download it. But you don't really need to do that because it all loads pretty quickly on the hub, but it's up to you. Any other questions before I move on and start talking about the actual projects?
It took me a moment to clone everything onto it. Is there a way we can get like a copy of the code onto the Slack just so we can catch up on that too?
The code in this notebook, you mean?
Yes.
I can once I'm done here, I can post it on the Slack.
Awesome, thank you.
Yep, no problem. Okay. So at this point, I'm going to go back to that analysis.ipynb notebook in the project template, or the week 1 project repository that I cloned. So here's the big picture of the projects. There's a data set called the reproducible brain charts dataset. RBC. Long story short, it's a collection of different data sets, including a data set called the Philadelphia Neurodevelopment Cohort. Has anyone heard of this data set or used it before? Oh, perfect. No one's used it. That's exactly what we wanted. Okay, so the Philadelphia Neurodevelopment Cohort data set includes a bunch of scans from a bunch of people of different ages. They completed not only a whole bunch of MRI scans, but also a battery of clinical assessments. And as part of the RBC data set, those clinical assessments were analyzed with what's called a bifactor analysis. The details of this analysis are not really important for this project necessarily, but if you want to read more about it, there's some links in the text here that can explain lots of detail about what those analyses were. The point of the analysis was they took this battery of clinical assessments and basically reduced it down to a single P factor, which is a generalized psychopathology score across all the participants based on this battery of tests. As well as a set of orthogonal measurements that are related. So every participant in this data set has this big set of scan data as well as a generalized psychopathology score. Your task is to take this data set and whatever data you want from it and predict the P factor or the generalized psychopathology factor for a set of subjects that we have left out of the data set. So I'll show you in a minute, but basically we've created a training set of subjects who have their P factors listed in the data set file, and we've created a test data set who do not have their P factors listed in the data set file. And your job is to come up with some way to model the P factor based on the training data set and then predict it in the test data set. And you'll submit those predictions of the P factor on Friday, and we'll go over that on Friday. Questions about the general set? Awesome. Okay, so this notebook just walks through our very simple approach to solving this problem. And what we did was we just took, we did a very simple model. We pulled out Brodmann's area 1 surface area for every subject in the data set. And we did a linear regression between the Brodmann area 1 surface area and the P factor and made predictions based on that. There's a lot of reasons to believe that that will not be a good model, and I'm not going to tell you how well it does on the test data until all of you have turned in your answers. But suffice to say that this is a very simple model just intended to kind of demonstrate the problem. Okay, so again, the notebook goes through all these, how we, like this notebook solves the problem as we did it. But I'll just walk through it, and I'll be kind of quick because I want you guys to have time to work on your projects this morning a little bit before our break. But just know that if you have any questions or you have any trouble in the projects at all, Ariel and I, as well as John and Kelly and Mackenzie, who've been helping so far, will be around to help you out with any issues you have or any confusion you have. Just let us know. You can send us messages, or if you're some of the groups that are here, just find us during the project time and we'll be glad to help. Okay, so the first thing this notebook does is import something called RBC path from RBClib. This, long story short, the RBC dataset lives on S3, but it lives on S3 in a kind of weird way. It uses a tool called DataLab, which is honestly a great tool for managing datasets. But because of that, it's got a kind of weird relationship with S3 where it's partly on GitHub and partly on S3. And we didn't want you all to have to worry about that very much. So this RBC path is a custom kind of cloud path that works for the RBC dataset. Question? No, sorry. Okay. So instead of cloud path, you'll be using RBC path, but otherwise it's the same type. It's a cloud path. We import pathlib and we import pandas and numpy because we're going to be looking at some data frames in this data set. The Philadelphia Neurodevelopment Cohort, or the PNC data set, which we're going to be looking at specifically, has 3 sub data sets that are one for the free surfer analysis. So this is like anatomical analysis of the subjects. one that contains all the raw data in the brain imaging data structure, or BIDS format, and one that contains preprocessed functional MRI data, mostly connectivity data. You are welcome to use any of the data in any of these repositories, but because especially the BIDS data is not processed, you are really probably not going to have time to go and process raw scan data. So we're going to kind of encourage you to focus mostly on the FreeSurfer data. But you're welcome to use whatever data you want. It's totally up to you. Okay, so kind of as an example here, if we want to look at this particular subject, this is just a subject ID from the data set, and I'll show you where to find these in a second. We can create a subject path using this RBC path type, just like we did a cloud path. And we just basically say RBC://, and then you put one of these sub data sets, PNC FreeSurfer, PNC BIDS, or PNC CPAC, and then whatever subpath of that data set. If you want to know where these data sets live, there's a link somewhere up here, but basically you can go to GitHub /repro brain chart. This is the reproducible brain chart GitHub organization, and they have repositories listed here. And if you click on these, you can find the repositories that start with PNC, for example, PNC BIDS here, or let's find the PNC FreeSurfer one. This GitHub has all the files listed, but if you tried to clone this GitHub, you wouldn't actually get the files because they're actually stored in GitHub large file storage. And that's why we use the RBC path type. But all the subjects are here and all the files are here. So if you just want to browse the data set, you can browse it in this GitHub repository. Okay, so here we have a path to the FreeSurfer sub data set, the FreeSurfer directory /sub - this subject ID. So just to quickly show you where that comes from, if I go back to the PNC FreeSurfer repository, here I'm in the FreeSurfer subdirectory, and then here I'm in that subject's data subdirectory. And you can see that there's a few files here. And several of these are zip files because they contain like the whole FreeSurfer output. We're just going to focus on this TSV file, a tab separated value file, that contains just the kind of summary information about the surface areas of different regions and such based on FreeSurfer's output. So here I make the subject path just to their directory. I just assert that it's a directory to make sure we got the path right. And then I say for each file in the directory, just print out whoops, I didn't import the libraries. Sorry, for each file, just print out its name. And you see we get this list of all of those files in that directory that we were just looking at. Okay, so down here, we take that region surface stats.tsv file I just mentioned for this subject, and make a file path for that subject. And then here, I just print out a message, and then like we did earlier in the path example, I say stats file path dot open. This R means I want to open it for reading as F, and then data equals pandas dot read CSV, and I import the tab separated value file using pandas, telling pandas that we have a tab as a separator, and it pretty quickly loaded in this pandas data frame that for this subject contains all kinds of information. So there's basically a data frame where we have the same subject ID for all columns because this is just this subject's data frame. And then we have a bunch of different anatomical atlases, each of which have different brain regions that they identify. So for example, here, if you want to know the size of the cuneus for this subject based on this atlas, it's over here in the gray volume or the surface area, which are both reported in millimeters squared and millimeters cubed. Okay, this data frame contains a whole bunch of condensed surface area and brain volume data for different regions. So we just downloaded one of these files here. Okay. We'll come back to this subject in just, well, okay, actually, I'm going to skip this next section. No, never mind. We'll come back to the subject in just a minute. Sorry. Okay, so the next kind of important thing that you need to know is who are the participants in this subject study, and who have we allocated as part of the training data set, and who have we allocated as part of the test data set. There are a couple files just on the hub in the shared data directory that give you that information. And this cell tells you how. Basically, in just a normal file system path in home Jovian shared data RBC, there's a trained participants and a test participants TSV files. So here we just make a path to that directory and then make paths to both of those files. And then we just read them both in with pandas like we did up above. And then we concatenate the two data frames into one big data frame and just display that at the end. And basically this has a participant ID, the study, which is always going to be PNC. There's information about the session, their age, some general demographic data about these subjects. And eventually somewhere in here, there is a column for P factor. This is the factor you're trying to predict. And you notice that these subjects, because they're training subjects, all have P factors listed here. There's also a few other those orthogonal measures found by the bifactor analysis are also in here. But we suspect you won't be able to predict the P factor very well using those because they're orthogonal. Regardless, we've got the P factor. Any subject that has a P factor is part of the training data set. Similarly, all the subjects who are in the training data set file are obviously training data set subjects. All the subjects who have, all the subjects whose P factor is not a number are test subjects. So those subjects are the ones you're trying to predict, whose P factor you're trying to predict. Okay, so I'll go over this kind of briefly, but basically for this section contains our kind of quick and dirty solution to this, this challenge. The first thing we did was we wanted to collect all the data into one big kind of data frame or one place on our hub directories. So we wrote a little function called load freesurfer data or load fs data that takes a participant ID and optionally a local cache directory where you want to store this semi-permanently. Basically it just creates a path, finds that subject's subdirectory inside of the freesurfer repository, and then finds that region surface stats for that subject, loads it in and returns it. So this just does as a function what we did up here where we loaded in that file. Okay, so then let me run this. So then here's just to test that. Here's an example participant ID. Let's make sure that this loads in the data frame of freesurfer data. And there it is. So that seems to be working. And you all are welcome to use these functions in your projects. Feel free. Okay, so then we wanted to extract the Brodmann area 1 region, and Brodmann area is encoded as Brodmann.1 in the struct name column of this data frame. And so if you extract those rows, you get a left hemisphere and a right hemisphere Brodmann area 1. And each of these have surface areas in square millimeters here. So we can extract those surface areas from the data frame we just loaded, and we just decided to sum them up to make a bilateral Brodmann area 1 surface area. Okay, so we can do that, but we need to do that for each subject. So again, we're going to write a little function that loads the Brodmann area 1 surface area for a participant ID. And it starts by just loading in that data frame using the function we just wrote. And then does what we just did up here, pulls out the Brodmann area labels, adds up their surface areas and returns the bilateral Brodmann area 1 surface area. So we can test that on our example participant and make sure that it works, and it seems to work just fine. Okay, so the next thing we needed to do is to build up a data frame of all the participants, their Brodmann area surface 1, and their P factors. So that's what we do in this this cell. I won't belabor this right now. Really, all it's doing is it's going through each row of the subject's data frame and building up a new data frame that has their participant ID, their Brodmann area surface 1 by using that function we just wrote. and their p factor by pulling that out of the subject's data frame. Now, when I run this, it's actually going to take a while because there are thousands of subjects. So this is a fairly large data set in terms of subjects. And even though each file only takes a few seconds to download, it's still going to take a few minutes for this to run. And so there's a little progress bar here that I put in there to show it. We're not going to finish this right now. It's going to take 5-10 minutes maybe to get all the data down. Okay, this next cell is the whole machine learning solution we implemented. What I expect for all of you, what all of you will find is that wrangling the data and getting it in the right format for whatever you decide to do is going to be most of the work. And that's just the reality of data science most of the time, is that getting the data organized into a way that you can use is at least half the work, if not 90% of the work of a project. So here we're just using the scikit-learn linear model package and the linear regression type, which does all the linear regression details for you. We created a training matrix by pulling out the Brodmann area 1 and the p factor. The linear regression doesn't care about the subject ID. We pull out we figure out which rows have nans, because those rows are test subjects, not training subjects for the p-value. And then we pull out just the training subjects to make a big matrix with a whole bunch of columns, a whole bunch of rows, one for each training subject, and 2 columns, one for the Brodmann area surface 1 here, and one for the p factor. We then give the Brodmann area surface 1 as a matrix into a linear regression object, and we give the p factor as the predictions. And this linear regression type will do the training for you. It will fit the model. And then we can just can just print out the results here. Since it's still loading the data, I'm not going to do this right now. But this will basically train the model and can tell you the intercept and slope for the model. And then finally, we take our test matrix, which we extract the same way, but we only need the Brodmann's area 1 surface areas because we're predicting the p factor. We pull out the test subjects, and then we ask our linear regression model to predict the p factor for the Brodmann area based on the Brodmann area 1 surface areas of our test subjects. Again, since we're still loading the data, I'm not going to run this right now. But if you run this later, you'll see how it works, and it produces predictions. I'm not going to say they're good predictions, but it produces predictions that look like they could be p factors. Okay, if you get to this point, we'll talk about step 4 and how to save the results and submit them back to us on Friday, which is the day we'll ask you to turn in the projects. You'll have until the end of the day on Friday to turn them in. But this is basically the assignment, is to come up with some way to predict the p factor based on whatever data you want to use out of the PNC data set. Okay. Any questions, big picture questions or specific questions that I can answer right now? All right. So I encourage you all to, so we've got about 20 minutes till our coffee break, and then we'll be back here with Serge speaking at 10:30. What I want you all to do right now is go to the rooms you're assigned based on your group, get to know each other. Most of you, everyone except for the courtyard group has online participants in their group. So please, there should be an owl set up wherever you're going. So please check in with your online participants. Just keep in mind that not everyone is attending at the same time exactly. If you have some people in your group who don't seem to be around, don't worry too much about it. It's kind of their job to sync up with you. You've all got channels, but you know, if people are messaging you on some other schedule and want to help, please work with them. If you are finding that something happened and your group is too small or something like that, message me. Or if you didn't get assigned to a group, message me. But otherwise, this is the project, and we'll be around to help. There's time for this throughout the next few days. Have at it.